We already know how to calculate limits that are a very small number divided by a very small number, a 0 over 0 form. So we've seen lHpital's rule for the situation when the limit of the numerator and the limit of the denominator are both 0. But it turns out that lHpital's rule is also valid when the limit of the numerator and the limit of the denominator are both infinity. I mean, you've still got all these other conditions. You've got to check that the limit of the ratio of the derivatives exists and that the derivative of the denominator is not 0 for values of x near a. But given these conditions, you then get the same fantastic conclusion that the limit of f over g is the limit of the derivative of f over the derivative of g. Let's take a look at an example. Well, here's an example. This is an example you really don't need to use lHpital on, but at least it demonstrates what the technique is. The limit of the numerator is infinity, the limit of the denominator is also infinity, though that's maybe a little bit harder to see, and consequently we could use lHpital, and it would tell us to compute instead the derivative of the numerator, which is 4x plus 0, divided by the derivative of the denominator, which is 6x minus 1. Now, can I calculate the limit of this as x approaches infinity? Yes, of course I could just do this directly too, but I could again use lHpital if I really wanted to. The limit of the numerator is infinity, the limit of the denominator is infinity, so lHpital tells me to instead consider the ratio of derivatives. The derivative of the numerator is 4, the derivative of the denominator is 6, and now I'm in a situation where I'm just taking the limit of a constant over a constant. That means that limit is 4/6, which then tells me how to compute the original limit. But I mean, this isn't the best way to do this problem, but at least it demonstrates that you could use lHpital in a situation where you've got infinity over infinity. But not every limit is something going to 0 or something going to 0 or something going to infinity over something going to infinity. Sometimes you might have a limit where it's a product. The first term is heading towards 0 and the second term is heading towards infinity. For example, here I'm asking about the limit as x approaches infinity of sine of 1 over x times x. This first term, sine of 1 over x, that's getting close to 0 when x is very large. And the second term, just the x, that's getting very big. So this first term is having a tendency to make this quantity smaller, but the second term is having a tendency to make the quantity bigger. You know, who wins? Well, with lHpital, the only thing that we can really deal with is sort of a 0 over 0 situation or an infinity over infinity situation, and that's neither of these. But we can transform this problem into one of these situations. So instead of calculating this limit, I'll calculate the equivalent problem, the limit as x approaches infinity of sine 1 over x in the numerator divided by 1 over x. So instead of multiplying by something which is going towards infinity, I'm going to divide by its reciprocal. The reciprocal of something going to infinity is going to 0. So now I've got a situation where the numerator is going to 0 and the denominator is going to 0, and this problem, equivalent to the original problem, is now amenable to lHpital's rule. So by lHpital's rule, I would want to differentiate the numerator, differentiate the denominator, and then look at that limit to try to understand this original limit. Well, what's the derivative of sine of 1 over x? It's cosine of 1 over x, because the derivative of sine is cosine, times the derivative of the inside, which is minus 1 over x squared. And I'm going to divide by the derivative of the denominator, which is minus 1 over x squared. So now how do I evaluate this limit? Well, the good news is that I've got a minus 1 over x squared in the numerator and a minus 1 over x squared in the denominator. So this limit is the same as the limit as x approaches infinity of just cosine of 1 over x. But now 1 over x is getting very close to 0, and what's cosine of a number close to 0? It's 1. So this original limit is 1. You might have something near 1 being raised to a very high power. Here's an example. The limit as x approaches infinity of 1 plus 1 over x raised to the xth power. So for very large values of x, the base here, 1 plus 1 over x, that's close to 1. But the exponent is very large. If you take a number close to 1 and raise it to a very high power, it's actually unclear what you're going to get. Depending as to how quickly this is moving towards 1 and how quickly this thing is growing, you get wildly different answers. Now this is not 0 over 0 or infinity over infinity. So I've got to transform this problem into something that lHpital can handle. The trick here is to use exponential functions. So I'm going to rewrite this as e to the log of the limit as x approaches infinity of 1 plus 1 over x to the xth power. E to the log of something does nothing, right? These are inverse functions. But log of a limit is the limit of the log. So this is e to the limit as x approaches infinity of the log of 1 plus 1 over x to the xth power. Now log of something to a power is that power times the log. So this is e to the limit as x approaches infinity of x times the log of 1 plus 1 over x. Now what kind of situation am I in here? X is very large, but log of a number close to 1 is close to 0. This is big number times number close to 0. That's the infinity times 0 indeterminate form. So how am I going to handle this? Well, we just saw a minute ago that I'm going to handle this by putting the infinity in the denominator with the reciprocals to make this 0 over 0, the sort of thing that lHpital can handle. So this is e to the limit as x approaches infinity of log 1 plus 1 over x divided by 1 over x. This is the same as this, but now I've got something approaching 0 divided by something approaching 0. This is the sort of situation that lHpital can help me with. This is e to the limit by lHpital, the derivative of the numerator divided by the derivative of the denominator. The derivative of log is 1 over the inside function times the derivative of the inside, which is minus 1 over x squared, divided by, what's the derivative of 1 over x? Well, it's the same thing here, minus 1 over x squared, and this is the limit as x approaches infinity. Now I've got a minus 1 over x squared, which cancels with a minus 1 over x squared in the denominator, and I've got 1 over 1 plus 1 over x as x approaches infinity. This is getting very close to 1. So this is e to the first power, which is e. And that means that this original limit, the limit of 1 plus 1 over x to the x power as x approaches infinity, is equal to e. Or you might have a very large number being raised to a very small power. For example, let's say I want to calculate the limit as x approaches infinity of x to the 1 over xth power. So the base here is very large, which have a tendency to make this number very big, but the exponent is getting close to 0, which would have a tendency to pull this back down closer to 1. So what is this? Well, we can try to transform this into this sort of limit problem that lHpital can handle, and I can again do that with exponential functions. So I can rewrite this as e to the log of the limit of x to the 1 over xth power, and this is the limit as x approaches infinity. Now this is the log of a limit, which is the limit of the log of x to the 1 over xth power, and this is the limit as x approaches infinity. But the log of something to a power is that power, so 1 over x, times the log of the base as x approaches infinity. Now I've got 1 over x, which is a number close to 0, times log of x, which is a very large number. This is 0 times infinity, so to speak. So I should try to transform this indeterminate form into something that lHpital can handle. So I could write this as e to the limit of x approaching infinity of, say, log x over x. This is infinity over infinity, so to speak. That's the sort of thing that lHpital is okay with. So instead of taking this limit, I could look at the ratio of the derivatives. The derivative of log x is 1 over x. The derivative of x is 1. So I should look at the limit of 1 over x over 1 as x approaches infinity. Well, that limit is 0, and e to the 0 is 1. So the limit of x to the 1 over x as x approaches infinity is equal to 1. Or you might have a limit that looks like something going to infinity minus something going to infinity. So let's try to compute the limit as x approaches infinity of the square root of x squared plus x minus x. So this is a very large number minus a very large number, the infinity minus infinity situation. So I should try to factor this or rewrite this to get it into a 0 over 0 or infinity over infinity, the sort of thing I could apply lHpital to. So I could try to pull out an x from this because x is going to infinity. I know x is a large positive number here. So I could rewrite this as x times, so what if I pull out an x from here? That's the square root of 1 plus 1 over x minus, when I pull out an x from here, I get minus 1. So really, this limit for large values of x, so as x approaches infinity, is the same as x times this quantity, the square root of 1 plus 1 over x minus 1. This is a large number. What do I know about this number? Well, this is the square root of 1 plus the reciprocal of a large number. This is close to 1 minus 1. This second term is close to 0. This is infinity times 0 in determinate form. So I could rewrite this using our standard trick as 1 plus 1 over x minus 1. So this is now the numerator. This thing's going to 0 divided by 1 over x, the reciprocal of this, but I'm dividing by it, and that's the same as multiplying. So now I've got 0 divided by a number close to 0, right? It's 0 over 0 in determinate form. So lHpital tells me I can analyze this by looking at the ratio of the derivatives. So I should look at the limit as x approaches infinity of, what's the derivative of this? Well, the derivative of the square root is 1 over 2 square root of the inside function, 1 plus 1 over x, times the derivative of the inside function, so the derivative of 1 over x, and I don't have to worry about the minus 1 because the derivative of that's 0, and then I divide by the derivative of the denominator, so I'll just write derivative 1 over x. So now I've got derivative 1 over x in the numerator, derivative 1 over x in the denominator. This limit then should be the same as just the limit of this. So I should be looking at the limit as x approaches infinity of 1 over 2 square root of 1 plus 1 over x. Well, what's 1 plus 1 over x as x approaches infinity? That's just 1. So this is 1 over 2 square root of a number close to 1. This is 1/2. And indeed, this original limit really is 1/2. I mean, honestly, we didn't need lHpital to calculate that, but we could use lHpital if we wanted to evaluate this limit.
Okay, let's summarize all the possibilities.
So here's a summary of everything you might see in the wild. If you see 0 over 0 or infinity over infinity in a limit problem, you can just apply lHpital in that case. But here I've listed off some of the other things that you might see. And these equations are sort of nonsense equations, right? But I hope they kind of tell you what you should do. So if you see, say, 0 times infinity in a limit, and by that I mean it's a product of things, one of which is limit 0, the other of which has limit infinity, well, you should transform this into one of these cases so you can apply lHpital. So you could do that by moving the 0 into the denominator and taking its reciprocal. This is really infinity over infinity. Or you could move the infinity in the denominator and take its reciprocal, and now you've got 0 over 0. If you see 1 to a very large power, or something close to 1 to a large power, right, you can use e to the log to transform this. And e to the log of this is e to the large number times log of number close to 1. Log of a number close to 1 is close to 0. This is an infinity times 0 indeterminate form. But you know how to handle those because you can convert them back into these cases, which you can then use lHpital on. If you see infinity to the 0, well, you could use the same e to the log trick, and then the exponent here is 0 times log of a big number, or a number close to 0 times log of a big number. But this is the 0 times infinity indeterminate form, which is right here, which you transform into these cases, which you then use lHpital on. If you see 0 to the 0, by which I mean a number close to 0 raised to a power close to 0, you can again use the e to the log trick, and this is e to a number close to 0 times log of a number close to 0. What's log of a very small number? That's very negative. So this exponent is again the 0 times infinity indeterminate form, which you can then convert into this and apply lHpital to it. The last case is this infinity minus infinity case. And there, one thing you could try to do is put it over some common denominator. So I'm thinking of the common denominator here as being 1 over the product of these two terms. And here I've got 1 over the second term minus 1 over the first term. But the point here is that you can rewrite this difference of very large quantities as, say, something getting close to 0 divided by something getting close to 0, which is the sort of thing that you can then apply lHpital